Hello, and welcome to our conversation, Designing Scalable AI Clusters, Architecture and Networking for Multiple Site Deployments. I'm here today with Raymond Chik, Vice Chair of the IEEE AI Hardware and Infrastructure Working Group, and Clayton Wagar, Principal Consulting Engineer for AI and HPC at Nokia. Welcome to everybody. Thank you for joining. At the end of our session, we will take questions, so please feel free to put your questions in the chat box, and we will make sure to address those questions. So, Raymond, I'm going to start with you. Many companies focus on speed and performance without thinking much of, about power and efficiency, but now the architecture has to be configured from a performance and latency perspective. So what is your number one concern right now in terms of compute and the challenges of power and energy? If you could give us a high-level view.
Yes, sure. Thank you, Susana. And thank you, everyone, to attend this discussion. In terms of AI compute power, that is a major concern right now, obviously, because over the past 6 months or a year, everybody seems to be talking about how power is important, and AI compute is consuming a huge amount of power. People are building gigawatts data centers. People are concerned about how are we going to be powering these data centers. And in fact, power has always been a concern from my perspective. I started getting into the AI compute business about 8-9 years ago, and that's what I and my co-founder of my company trying to tackle. The reason why we are thinking power is a big concern was that we realized that at least from my perspective, because I'm a chip guy, so I look at the things at that level. Most of the power that is concerned in all these AI compute actually are burned through data movement, and either across through network, through your 6G, shipping a bit from your car to your data center to do some analysis costs a huge amount of energy just by sending the bit over. And by the same token, in the compute world, in the chip world, we also are very concerned about the energy between the compute and memory. Moving the bits between the memory and the compute costs a huge amount of energy, and in fact, so much so that the compute power, when you try to optimize it to a lower level, it's becoming less important as compared to shipping the bits around, depending on what kind of workloads you're talking about. And I'm thinking mostly nowadays the LLM large language models. So when we architect a AI compute system, we think about not only the compute, but also memory, how to ship between the data between the memory and the compute. And from a scale up and scale out perspective, how do we connect all these AI compute engines together from server to server, rack to rack, and even from data center to data center. So from a low-level chip up to AI cluster, data center architecture perspective, we all have to think about how do we efficiently minimize a data transfer between all these nodes. And so that's kind of how my perspective of a power consumption with the modern day AI compute.
And Clayton, do you want to add from your perspective at Nokia, what is your perspective on that right now in terms of?
Yeah, well, I think building on what Raymond said, the thing about AI clusters is that they're unlike traditional cloud. Traditional cloud, we can make elastic and the workloads run in parallel with some load balancing, if you will, and a simple explanation. And we can diffuse that power over a number of, a site, 2 sites across the floor of a single data center. With AI, of course, it's a coherent process. It requires all of this equipment to be working in tandem together, which is why the interconnect, the network, is such a critical part of it. It's not simply that we get the elasticity and growth out of it. It is a fundamental part of how AI works and how we're able to train and leverage these very large language models, generative AI models. And so power is a fundamental concern. If I look back at history and we look at traditional networks like enterprise networks and service provider networks, power was always very important because it led to operational expenditure. And so we wanted to minimize that. So we had programs as vendors and in the community to minimize that power from a expense standpoint. Now the trade-off is the less power we consume in the networking, the more we can invest in the thing that is doing the work, which is the GPU, the accelerator, whatever it happens to be. And so by saving the power in the network or being as efficient as possible in the network, then you have the ability to deploy more of the GPUs, more of the accelerators, and again, ostensibly, that's where the revenue is, where you're making your money. So power is a leading concern, not just from acquisition of power in order to grow AI. We see it in the news, all of the massive number of gigawatts being contracted around the globe. Right. But it's also necessary just to provide for the efficient operation of the AI cluster itself.
And as that happens, since power is already a big problem, and we haven't even reached the performance thresholds, predicted for the next 2 years, what do you think will be the technology that will have a mitigating impact? Would it be optics, on the GPU or anything like that? Is there something on the horizon that excites you about solving this problem?
I think there's from a power standpoint, there's a couple things that are kind of the highest impact or highest leverage technologies. We have to first start with Ethernet itself, right? So AI has grown out of machine learning, out of high performance computing. It's this blend of technologies that's been pulled from a number of different domains, some of different disciplines over the past many decades. And as we brought it together, we have these very highly vertically integrated systems which perform very well, no question about that. Ethernet has really established itself here in 2025 as the dominant technology for internetworking between different parts of a GPU cluster, whether it's inside the rack itself, whether it's between the racks, whether it's across buildings. Ethernet and its more than half-century heritage and the number of participants in the market gives consumers, AI consumers, lots of choice, lots of procurement leverage, which they like. And so we start with Ethernet as kind of fundamental technology. Now, building on that, we are in an era today where everyone can see that AI systems are getting denser and denser. You have from the Hopper series to the Blackwell series and the upcoming Vera Rubin. AMD has their programs as well, the 300, the 400 series. We have this densification. We have racks that are consuming 25, 50, hundreds of thousands of watts of power. That's not, it's simply not, out of the ordinary to be dimensioning in these kind of scale. Right. And so we're doing that with electrical today. We're doing that with copper interconnects. But copper, of course, has a short reach. We can only do things within a rack. How do we? And by the way, so what we have now, when we see these giant data center projects that are being announced, we have huge floor space in a data center that's very poorly used because these things are so dense and they have to be placed distant from one another. You mentioned optical technologies. That's absolutely where we're going. We're going to have an electrical to optical transition over the next 2 to 5 years. It's going to be both within the scale-up networks, the scale-out networks, every one of those, and maybe we'll talk about those, but every one of those will be impacted by optical technologies in order to get to the power consumption that we know we need to get to. So very aggressive targets that most of the major customers have.
Okay. And Raymond, do you have anything you want to add to that part of the conversation? I know we were going to talk about, optical connectivity and silicon photonics and things like that. Is there anything that's exciting you that's on the horizon that you think will solve?
Absolutely. So I am completely agreeing with what Clayton is saying about the movement towards optical. And so being a chip guy, I sort of follow what's happening. Although I'm mostly in the compute, but I closely follow what's happening in the connectivity world, especially silicon photonics, where, as Clayton was saying, where do we transition between the logic and electrical and the optical fibers, optical communication, the lasers and whatnot. And Clayton talked about between racks, between servers, and that's kind of where things are happening. Interesting things are happening with interconnectivity. And traditionally, you would think copper is cheaper, laser-based, optical fiber communications are more expensive, and therefore there is an effort actually trying to extend the length of copper interconnect to keep the price as low as possible. The interesting I wouldn't say battlefield, but the ground of competing between optical and copper communications is kind of in between servers and in between racks, where you are having cables somewhere in between a couple of meters to 10 meters. That's where things are interesting things are happening. Specifically, I'm referring to if you're talking about passive copper wires, it doesn't really run more than a meter or two before it gets speed limitation and all that stuff. And then you start thinking about optical cables. But optical cables, you've got all these laser diodes, and these are more expensive components in order to feed those short meter or two cables. There are a newer class of cables that came out in the market in the recent 2 or 5 years, active electrical cables, where actually a company that I follow very closely is called Credo Technologies, where they actually sell these active electrical cables, where they are making a lot of headways into capturing the 2 to 10 meter kind of market in terms of providing very cheap copper cables, where they have electrical components, SerDes components inserted within the two ends of the plugs and connectors. So that actually created a very massive market for them. And obviously, as there's a physical limit of how far you can reach. So I'm pointing out this specifically length to 2 meter to 10 meter is interesting. Is an interesting distance, if you will, between connectivity. And beyond that, no doubt, it's optical. And when we talk about integrating electrical and optical components, the industry trend is a strong industry trend going towards co-packaged optics and logic components, and also fully integrated photonics into standard logic silicon. So those are the two pretty big driving force behind the industry to move towards. Cost, if you integrate these photonics and the logic components in the same silicon, that's kind of a bit far down the path. Technology, I know, is there, but from an economics integration perspective, it might still take a while for the industry to adopt. One major thing is probably the as compared to pluggable optics. Right now, what we're doing today, if some optical components the cable is bad and whatnot, you just unplug it and hot plug back in. So separating electrical and optical sort of separately, but if you integrate them together, you have to wait for the technology for the manufacturability to mature, to be able to make sure that they are reliable before you want to massively deploy it. But I think this is coming.
It's coming. And Clayton, is there anything you want to add to that before we move on?
Yeah, I would say from a vendor standpoint, this transition that we're talking about, Raymond outlined here, really revolves around some significant physics challenges. Make no mistake that the change in the construction of a network, especially the devices themselves, will change more radically over the next 5 years than it has over the last 20. You know, we've come from a world where we have fixed form factor, we have chassis-based systems with line cards and backplanes, and all of that has revolved around electrical. Well, now as we get into the speeds that we're seeing, the serial speeds, the SerDes speeds, the traces on the motherboards can only be of a very short length. They can't even reach to the front panel pluggables. Now, we have customers that for many, many decades have been comfortable with the pluggable idea. They have optionality. It's a well-known operational model. They have a lot of people that understand how to use it. But now we're experiencing physics challenges. So this idea of bringing optics into the system means we have to take that pluggable and look what's inside of it. Right. And figure out where all those important pieces go. How close can they go to the chip inside, right? How close can we get that laser inside? What kind of flexibility does that remove from the customer? There's going to be, by the way, there's not going to be a single winner here. There's going to be options. There's not just co-package optics, which has a big splash right now, and pluggables, which is traditional. There's things like LPO, right? Linear pluggable optics, which get you much of the power savings, but require some special design. So vendors like ourselves are going to have to undergo a change in our engineering discipline in order to support a lot of this new technology, which is necessary to unlock the gains that we're both talking about.
And in terms of that, you're talking about pluggability and does this affect skills and how, and how do companies get the skill sets and the expertise they need to do to do this? Is there a shortage in the industry right now, or do you feel there's are people keeping up on the necessary knowledge and skills to do what you're talking about here, which is kind of
Well, it's funny you mentioned that. I think in the entire, if you talk about data center builds, I just saw an article this morning, as a matter of fact, that there's a shortage of something like 500,000 tradesmen and women to put data centers together. So I'm certain that there's a workforce shortage on the people to manage and operate that equipment after you put it in. The reality is that with network automation and certainly with AI operations, which is leveraging AI itself to manage a network at the scale we're talking about, some of these systems we see out there have 1 million GPU. Microsoft announced Fairwater 2 weeks ago. The Atlanta site is about a quarter of a mile down the road from my house. So I know exactly what one of these buildings looks like. And to manage that inside is a level of complexity that's just impossible for a single human. So we think about using AI operations tools to augment the workforce, which, yes, we need more workforce for there's no question about that. As a network engineer for over 3 decades, I can tell you that for someone to come into my field, it's a pretty high burden. We have to learn the CLI for 5 or 6 or 7 different types of, vendors' equipment. We have to have all of these technical skills. AI is going to unlock that and open up a greater workforce, addressable workforce to our industry, because that burden will be lower, right? They'll be able to manage with natural language tools. So am I concerned? Yes, I always love to see more people in networking. I've been doing it a long time. I'm ready to hand off the baton at some point. But and I love it. It's a great field. But we do need more people in there to manage, because the networks are more complex, not necessarily because they're new technologies.
Okay. We do have a question that came in from one of the attendees. It says, in the realm of mobility, the connectivity of optics makes power more difficult. How is power gaining in rugged, reliable connections? Do either one of you want to take that question?
Well, I mean, in terms of power, I'll take the question. I do a little bit of work with our federal folks in Nokia, who have a 5G, private 5G, tactical 5G product. And so have been talking recently and doing some work around this idea of a continuum of AI that can live all the way out in the field and all the way into a sovereign data center in country, right? So battlefield to headquarters. And certainly power is a key part of that. I would say, in general, for rugged environments, if you're a utility, you're a mission critical, you're an enterprise that needs to put it in these environments, access to power and management of power is going to be a key issue. What's not clear at this point is, again, that continuum of AI and open compute is kind of taking a look at this area as a possible new area of exploration. Looking at those challenging environments, power availability certainly has to be there. Optimization of power, yeah, for sure. But I think that's going to be largely on a device basis. So like a tactical device or a handset or something like that. I think that's where you'll see the big power savings, because as you diffuse AI to the edge, you'll need to capture those power savings out at the edge where it's being run.
Okay. And I didn't yet ask Raymond, since, you're with the IEEE, what is it that's happening, that's worth mentioning in terms of standardization, maybe of interconnects or a roadmap for silicon photonics? Is there any interesting work that people should check out within the IEEE?
Yeah, I guess from what I'm directly involved with in terms of the IEEE, which is the AI hardware infrastructure working group, which is underneath the AI Coalition banner. Now, this particular working group that I'm involved in has less to do with standardization, because there are other works around in the AI Coalition that looks at that. But in terms of anything about infrastructure and connectivity and silicon photonics, certainly is something that we will, it's part of our mandate to cover in terms of study and roadmap, and by webinars. We're also putting on webinars that talks about these kind of things. And perhaps check out the AI Coalition webpage and look for resources there.
Okay. And Clayton, in terms of any emerging technologies that you haven't mentioned yet that you think are, going to address some of the problems around power or memory, is there anything else you want to mention? I was reading recently about like RRAM, or compute and memory architectures. Anything evolving there that's of interest?
Well, I think the next phase, as we get to this era where we have more flexibility in the physical design as well as the logical design of these systems, optics unlocking a lot of that. We enter into a wave where we're going from today about 30% of networks are built for inference, and about 70% are spent for training. This is why you see the heavy spend on the part of the hyperscalers, the frontier labs. But we know that about 5 years from now, it's going to be inverted, right? A majority of the spend is going to be on inference infrastructure as we put these AI models to work, as they promise to go to work for us in a number of different key areas. So, as we move to that, we're looking towards a number of key technologies. Number one, the orchestration of those workloads. So there's kind of a software domain here. How do we automate all that? I mentioned AI operations before. From a practical standpoint, Nokia participates. We're a big believer in open standards. We're looking at this from an any-to-any world, and so we end up driving a lot of the things that happen in the standards organization. A lot of your audience may only be familiar with Nokia as a telco company, right? Or maybe be looking for the mobile phone that we don't make anymore. We haven't made for 15 years, but everyone loves their old Nokia phone. In fact, data center and hyperscale and AI is a very big business for us. Data center fabric solutions as well as a routing product line. So we like to drive the industry forward through opportunities. IEEE is one of those. IETF, Ultra Ethernet Consortium, we've been active there, as well as the Open Compute Foundation, as well, the Open Compute Project. So we see a lot of the high leverage technologies as being those that the industry itself and customers themselves help define. We think that those have the best chance of succeeding and offer the lowest risk for participants in the market.
Okay.
I have some comments about Susana when you mentioned the memory technology and RM and such. That's what you were also mentioning earlier, right, Susana?
Yes.
So I personally, my day job actually is in energy efficient AI compute. In a particular architecture that we're working on is called at memory or neo memory architecture. So it's very memory related, the work that I'm doing. And specifically when you mention RM and different types of memory, that leads me to think about a class of architecture that is called in-memory compute. And the idea is, again, it's very compute centric, but it's very related to power and very related to minimizing data traffic in a micro level, not on a network level, but on the board, the traffic between compute and memory. So all these ideas and memory-centric architectures is really to try to bring computation and memory very, very closely knitted together in terms of if you think of a standard compute architecture as a von Neumann architecture, where a CPU and memory kind of separate entities,
right?
Ship a address across a bus, and then the memory randomly access the byte or the data back to the CPU, and that traffic is it's still kind of a micro level networking. It's still a lot of energy wasted there, and the idea of all whole class of memory centric architecture is trying to fuse them together as closely as possible. And so that's a very central way of a lot of new startups and new companies are going in that direction. So that's kind of what I wanted to comment on.
Thank you. There's another question here. It says, as AI clusters scale across multiple data centers, what's the biggest architectural bottleneck you're seeing today? Compute placement, networking, or energy? And how should operators prioritize investments? Do either one of you want to take that question from one of our viewers?
Well, yeah. Well, I think this is an area that we're calling scale across, right? So this is the idea where you can't make a single building large enough, or you don't want to, or you have other requirements which have you using separate buildings, could be, or separate sites installation. And Meta infamously uses tents, right? So they build their giant cluster using semi-permanent tents. Doesn't really matter. The idea is that we want to capture either network connectivity or power availability or have some kind of optionality. So scale across, obviously the biggest thing is providing the bandwidth, right? The AI is extraordinarily bandwidth intensive. And if you intend to do robust jobs between two different locations, you're going to have an extraordinary amount of bandwidth. Back to the point of optics, they all have certain reach sizes. So what you're seeing is most of the large consumers using ZR technologies, right? So 800, 400 ZR, ZR plus. And so that it's the ability to extend that bandwidth between buildings. And make no mistake, we're not talking about one or two or three or four 800 gig links. We're talking about hundreds or thousands in the largest cases. The most discriminating consumers are providing incredible amounts of bandwidth between facilities. Then on top of that, of course, there's some features you need to manage the congestion control and provide the kind of SLAs, the kind of guarantees that you need between the buildings. But the key element really is providing that the bandwidth between buildings. Remember, this is almost like a LAN extension. If you're old like me, you know that word, LAN extension between buildings. It's not like data center interconnect, which gives you more multi-tenancy, more peering, some other more high sophisticated services. Scale across and connecting these clusters into one big cluster is absolutely all about the bandwidth.
Okay. And so there, it seems like there's a similar, it says, as AI clusters scale across multiple data centers, what's the biggest architectural bottleneck? And how should operators prioritize investments? And then there's another one here about asking about energy efficiency is becoming critical. What design choices in cluster architecture have the biggest direct impact on reducing energy per training run? So a little deeper dive there. Do either one of you want to take that one?
Well, I might first offer in terms of efficiency, architecture-wise, we have been talking mostly about hardware infrastructure, but the whole AI deployment is not just hardware, obviously, because I'm a hardware guy. I love talking about hardware, but it also has to do with the software side, the data science, the model efficiency. I keep thinking about what. Maybe it's a little bit political here, but what China has done, the great models, DeepSeeks, the QN models, they're highly, highly efficient. And meaning that it's not only the hardware infrastructure needs to be efficient, but also we need to think about the application level, the model level, how people think about efficiency. And that also is obviously tightly related to the hardware platform they're building on. And one thing that I keep thinking back is when DeepSeek first came out, when we looked at the paper, we were quite impressed what they've done. Well, very clever, but one thing they've pretty impressive done was they actually skipped their stuff was trained on GPUs, obviously not the highest grade GPUs advertised, but they completely skipped the CUDA software stack. So they dove right down into the hardware architecture and optimized their algorithm, their model that way. So from my perspective, it's sort of like driving a stick shift car versus a auto car.
Yeah.
So you optimize by actually doing the work. Not everybody knows how to drive a manual car, but you have to put in the time.
And someone in the last session had asked, if that type of efficiency that China is working on, will that kind of obsolete what the NVIDIAs of the world are doing? Will it leapfrog what we're doing right now?
I would say yes, but I think it's just a matter of in China they are forced to be more innovative and creative because they can't access the latest and greatest that what we can access here in North America. Mm-hmm. And so I think the mindset sort of in North America are changing based on that because we can't be too complacent here. Just relying on the abundance of the latest and greatest chip hardware technology. We need to also be thinking about at the higher level how we optimize the efficiency of the models and whatnot.
Right. And we have time for one more question. I have another question from. It says, what practical guidance can you share on balancing chip-to-chip bandwidth with memory bandwidth to avoid stalls in large-scale training? Either one.
Well, maybe because I'm a chip guy, so I'll just put in my 2 cents about when I think about the memory bandwidth between the compute, and by and large nowadays everybody uses, the big guys anyways, uses HBMs, high bandwidth memories, the AMDs of the world, and NVIDIA obviously. And the one thing about high bandwidth memory, to me, if you look at it deeper, it's really not very high bandwidth. If you are thinking about the use case of LLM, large language models, the models, the 200 gigabyte models, 80 gigabyte models, all these parameters has to sit somewhere. now they're sitting in HBMs. But if you have these 200 gigabytes of parameters sitting in HBMs, you have to stream all those through your GPU, every single tokens through all the parameters. And therefore, there's a ton of swapping between the memory and the compute, and that's everybody's bottleneck now, because it really is limited by whatever HBM technology that you are having access to. And there are new types of way of thinking about how to access DRAM, which is emerging now. It's 3D stacking. HBM is already 3D stacking, but you are now stacking compute dies with logic memory dies, and to make the connectivity a lot more parallel, and without going into much detail. So that's the point that I'm trying to make. There are people are thinking about ways to improve that.
Okay. And Clayton, is there anything you want to add to that before we wrap up? And I'd like to tell the panelists, the attendees, that if they want to ask you follow-up questions, they can find you on LinkedIn and ask any other questions. But is there anything you want to add, Clayton, before we sign out?
I'll simply finish by saying, Raymond was talking about a lot of exciting things that are going to happen. We hope to happen. There's a lot of investment in the research, but you talk about in-memory compute. You talk about optimizing communications paths, something like what DeepSeek did with parallelizing communications and compute. And every one of the things that we've mentioned today, disaggregated memory, storage, all of them require robust networking. I think that's the great thing, is no matter what we're talking about here, we're optimizing where these things happen. But at the end of the day, they're still all interconnected. And the fabric that interconnects them is that network, which is why it's an exciting time. Again, I've been doing this for 3 decades, and I'm really excited that sort of in the last act of my career, that networking is super cool again. It's like the late 90s all over again. It's the hottest thing, right? It was a little bit of a stepchild for a while, but we find ourselves working on some really exciting things that make AI happen. And very, very thrilled to be a part of this community and thrilled to be here today. Thanks for the invitation.
Yeah, we're living in an exciting time from a technology engineering perspective. I'm very excited.
Right. Thank you so much, Clayton, and thank you, Raymond, and thank you, everyone, for attending. I appreciate it.
Thank you.